So we'll look at scar hydraulic structures, focusing particularly on bridges, and bridges are very good. They encompass many aspects of other hydraulic structures. So bridges are useful, and the topic scar hydraulic structures is very large. Cool. So the bridge, as you see here, includes many aspects of other hydraulic structures. First of all, they contract channels, as we talked about yesterday, and they include generation of turbulent structures, change of the flow field, and so forth. And as I'll go along, I'll use variations of this particular figure. We have a typical bridge crossing, which we need to look at how scour develops. And first of all, it's contraction. The flow wants to eliminate the contraction, wants to open up that area. So the flow develops scour as a mechanism for doing that. Whenever you have a hydraulic structure put in a channel, it modifies the channel in some way or another. The designer needs to keep that in mind. So we have a bridge over a contraction. This is a low flow situation. You see the water level is relatively low. There's an old saying that person who overlook water under bridge will find bridge underwater eventually. And so again, it's one of these hydraulic structures and alluvial channels that requires continual observation and maintenance to be sure that everything works well. You don't walk away from it. This is the same channel at higher flow rate. It has abutments and has piers in the middle. The boundary is erodible. So it's like a spillway in a way, but the boundary and the sill is all erodible. And the flow wants to change it so that it opens it up a bit more. So it does that through elimination of the contraction scar and creation of scar itself. And so I'll talk about scar at abutments and piers and talk about some of the issues with regard to modeling, because as you can imagine, the erosion is both a hydraulic and a geotechnical combination phenomena and a structural phenomena too, because the bridge will adjust its structure, its position and shape. So other expertise is needed. First of all, bridge layout I'll talk about, scar at bridge piers and scar at abutments. Then I'll talk about some advances and challenges, particularly in similitude, geotechnical. How do you conclude that exactly in estimation of scar depth, instrumentation developments, and hybrid modeling, which includes both numerical and physical modeling. The idea is to have you present some thoughts which are provocative. One thought is that the Shields parameter that's often used for loose bed modeling leads to problems in modeling. And so you have to take those into account, as well as the various instrumentation that are developed. So we'll talk about scar bridges, and we'll talk about layout of bridges. So typically in a cross-section like this, we have abutments and piers. We have a rigid structure, the bridge deck, and erodible or flexible structure, the embankment, the approach to the bridge. And this part here is cheaper to build, so you'll find designers typically want to have the abutment approach as far as they can across the floodplain, shorten the bridge deck. So this is a rigid structure, this is erodible here, erodible on the bank, and erodible, of course, in the channel. So designers, to reduce costs, use an earth fill approach. This leads to problems. The erosion here is triggered by scar, but is a geotechnical failure as we go along. Typically, we have piers and abutments, as I've indicated, and the weakest point of any bridge is where you have a earth fill connecting with a rigid structure. Most bridges fail right here, and so there are lots of pictures of bridges that failed at this particular location. Sometimes the piers go as occasion. The flow field around a pier is very complex, as I'll explain and I'll show. Around the abutment, it's also very complex, but you, particularly scar here, you have geotechnical factors to consider. And so if we look at the layout also, be wary of this particular connection between an earth fill and a rigid structure. This is a problem with dams and levees. Whenever you have an earth fill structure connecting with a rigid structure, the joint is the weakest zone in the whole structure. So dams, levees, bridges will fail here if this is not adequately designed. Typically, you keep the pile cap lower than the bed level. These types of scar that can occur. One of the issues at the moment in estimation of bridge scar is how you combine these various scar aspects. And so CDOT, the Colorado DOT, at the moment doesn't bother about scar. It runs the piers all the way down, piles all the way down to rock. So you don't have to worry about scar. And that's okay for rocky mountain areas or mountainous areas where the rock is not too far down,
But if you get into the plains, the rock is at quite some depth, so you need friction-bearing piles like this, which I'll explain soon. So be wary of the joint between an earthfill and a rigid structure. That's the weakest point in the bridge. As I show here in this collage of photographs, and many of them are up the Big Thompson, this joint here, here, and here is the weakest point. The bridge is still standing, but this is on I-80. This is on the Big Thompson. The erosion here. The soil, when it gets saturated, as Piers pointed out, gets weaker. And so it doesn't have strength enough. The slope stability decreases. You have, in wintertime, you have freeze-thaw effects too, which open up gaps here. So the flow can easily percolate through there. So as is indicated through here, this is the weakest point. This is a bridge in Wyoming where the scarred blay or rock and went laterally and into the abutment. So this is a concern too, which we face in Wyoming and Colorado. This is another rendition of a bridge crossing. These days, typical abutments are set back on the floodplain to allow environmental passage, animal migration, or a service vehicle, a pickup truck. You have a passage up here, which allows these days deer and other creatures to wander through, and so the span is a little bit increased. But typically, we keep the first piers quite close to the abutment, as you see here, in order for less blockage for flow, debris hang up and so forth through there. And I have illustrations of that too. Bridging in an alluvial channel, you might have a situation like this one here, where the channel goes straight through. To be sure that the channel continues that way, and alluvial channels tend to shift from time to time, you might put a variety of control structures, in-stream structures, hard points, spur dikes, barbs, and so forth through here. You might include a guide bund to guide the flow through, in addition to those structures there. And this is an illustration of a channel with hard points and some riprap on the lower end to guide the flow through. Bridge opening. This is a location on the Missouri River too, where they've put very cheap structures to guide the flow through a bridge crossing. You can see the turbulence that's involved. And this is under I-80 in Iowa. You can see rock barbs on Indian Creek here to guide the flow underneath these bridges on I-80. Otherwise, the channel would migrate that way. So we have a bridge over the braided channel. These are problematic channels. Always braided channels are problematic channels for hydraulic structures. So a combination of a bund here, both sides, and spur dikes. And that one is a headed. It's got a head on the spur dike to try and guide the flow. Narrow contraction to reduce the cost of the bridge. You don't want to span the whole channel. This is a problem for road bridges, I find. Also, on the downstream side, problem in western Iowa is head cutting of streams due to channelization of dams on the Missouri, but channelization of the rivers generally. So you typically have flow directions down this way, some form of apron to arrest the head cutting so it doesn't migrate and undermine the bridge foundations of that. And so this is a bridge on a small county road in Iowa. And you can see the piles being undermined here. And the solution that was accepted was what's called a partially grouted ramp. Partially grouted is better than no grouting, because the rocks would tend to lift out for one reason or another. Also, the partially grouting is bordered by sheet pile bound in here. So this allows fish and amphibia passage and sediment passage. Before, they had the innovative design of what was called, in Iowa at least, a Greenwood bridge, where you combine a bridge and a weir. But you can see this blocks sediment passage and fish and amphibia passage. So these types of bridges are no longer used. So if you were to look at western Iowa, there are quite a few examples of partially grouted ramps and use of sheet pile fishways to allow fish to move up and down. We look at piers. We focus particularly on piers in the middle part of the bridge. And we also focus on, these parts are called abutment columns. These are like piers. So the bridge deck ends at an abutment column, which I'll explain a bit later. So this part here is a rigid part. And the flow field, as I will indicate in the next slides, is actually very complicated around a pier. First of all, pier form. If you work with most DOTs, there are standard pier forms. Iowa DOT, Colorado DOT, Nebraska DOT have standard piers for the size of the bridge. As I explain soon, what your job as a sediment engineer or hydraulic engineer would be is to determine basically how high the deck is and how long the friction-bearing piers would have to be. If you're dealing with a complicated pier, such for a big bridge across the Mississippi or across a large estuary, typically this is a one-off deal, which is you have some complicated form like this, which I would advise you'd have to do a physical hydraulic model to determine scour. But basically, as bridge sizes increase, the piers get more complicated in their form. Also, as I indicate in green here, there's a tendency these days to simplify the geometry, so less accumulation of woody debris or ice against that structure. So these types of multiple pile pier and or simple pier column like this. I'll explain the difference between a friction-bearing pile and a footing soon. These are very important. So your job as a hydraulic engineer is to design how high the deck should be. You need to know what the flood level will be at that particular site. Keep the pile cap, the part along the top there, below the bed level. As soon as the pile cap gets exposed, it is a broader, larger structure, and you can get deep scour. And your job is to figure out how, this is where you work with your geotechnical colleagues, how long these load-bearing piles should be. These are friction-bearing piles. If you remember from your geomechanics courses, two types of foundations typically. You have a footing, takes all the load, or you have a friction-bearing pile where the friction up the pile resists the load. So you need to figure out how long these would be, and scour has to be accommodated within the length. These are raked at some angle if there's some lateral loading, particularly through debris or flow drag on the pier. So your job is typically to figure out how high the deck is and how long the piles should be, friction-bearing piles. In Nebraska, the bridges, generally, road bridges are too low, in my opinion, as I'll explain in my next talk. So this is a county road in Iowa, a failed road bridge. The pier has been undermined there and it's tipped. You can have tip forward, backwards, sideways, just to illustrate very quickly the sort of problems that can arise. Typically for a friction-bearing pile, as I indicate here, you rely on friction force up the pile to resist the load, to balance the load or exceed the load. That's a friction-bearing pile. And you have this equation here in terms of pile length. So deep alluvium, such as on the plains in Iowa, Kansas, often you use friction-bearing piles because the rock or the stiff clay is way down. It's not economical to put a footing. In mountainous areas where rock is relatively at shallow depth, use a footing. So here, if you're building bridges in the Rockies or many parts of Wyoming, not all parts, it doesn't take long before you hit rock. You can found the bridge on the rock. This is a footing. Down here, you have a rock base, and you size the pressure to be within the allowable pressure for the particular rock or a stiff clay. So in mountainous terrain such as Colorado, Wyoming, for example, there's a lot of footing foundations on piers. Elsewhere, if the alluvium is deep, you use friction-bearing piles. So if we look at the boundary, we need to consider first the flow field and the type of material forming the boundary. And the flow field interaction with the boundary causes erosion. And this is a flume picture of a scour hole at a circular cylindrical pier. And there are complications that arise very quickly through woody debris and ice, as I'll explain soon, which both load the bridge and adjust the scour. And the flow field, which we'll look at first, is very complicated, as I will explain. So if you have to combine all of these, you very quickly end up in semi-empiricism. You know what's important, but there's no theoretical equation that handles all of these. So if we deal with the flow field, these are called junction flow fields, where you have a vertical structure bound on another structure. So a wing of an aircraft coming into the fuselage of the aircraft, a pier hitting a bed, called junction flow fields. And these are the most complicated flow fields that you can imagine. They're highly three-dimensional and they generate a lot of turbulence. So the flow field is very complicated here. So the flow field is causing scour. In early days, again, if I repeat the slide, we just focused on this part, the flow coming in, the horseshoe vortex, which was a phenomenon that was quickly realized. By the way, this is one of the easiest flume experiments to do. early experiments in labs dealt with putting a cylinder in a sand bed, figuring out what the scour depth would be. This is the simplest experiment that can be done. However, if you look at the flow, and these days we have the instrumentation to look at the turbulence that gets generated. And this is just a sketch of the turbulence. And this is where in the turbulence modeling that the hydraulic modeling starts to fall apart. It doesn't deal with turbulence that well. Also, we have erosion here, downflow here. We have a bow wave here, the horseshoe vortex, which generates other vortices, separation vortices. We have a depositional zone here, which tends to flatten out with time, an interaction of these turbulent structures, which are very complicated. So as we talked about with contraction scour yesterday, and Yong Lai knows this very well, this is quite a challenge to model numerically. Certainly, it's the simplest model to do physically, but without understanding the flow field. And so we have a whole range of turbulent structures, interaction of the turbulent structures, and a very complicated flow field, which the flow field changes in accordance with the flow depth and the diameter or some characteristic of the structure. And so typically we tend to divide them up again, as we often do. Narrow piers, very slender piers, where the Y upon D is greater than about 1.4 is the figure we use. Transitional piers in that range that I've indicated in number 2, and wide piers. And I'll show how the flow field varies a bit. Typically, you get the deeper scour for narrow piers, and as you decrease the flow depth, you get more frictional interaction of the energy dissipation of the turbulent structures. So these 3 flow fields illustrate shallowing of flows. So we have a deeper flow here. We allow the turbulent structures to develop. There's less energy dissipation. We decrease the flow depth. We have interaction of these turbulent structures. And we have very shallow flows where the bow wave starts to interact with the horseshoe vortex, you can imagine, and they're rotating opposite directions. They burn up a lot of energy, so we get less scour for shallower flows as we go through. As flow depth relative to the structure diameter decreases, we get less scour depth. So this is a deceptive problem. It's one of the first problems that was done in hydraulic laboratories, but the flow field is very complicated. If we have a very wide pier, for example, if the flow in a channel shifts, if the channel itself shifts so the flow hits the pier on the side, which we don't really want, we have a wider structure. On the other hand, we have a shallower structure. We tend to get a contraction scour that's deeper scour, instead of being in the middle, on the front, is on the sides, like this. So this is typical of a wide pier situation where the flow depth relative to the pier diameter is less than 0.2. These are approximate numbers, but give you a sense of what's important. They can happen readily with an uncontrolled alluvial channel, which can move around. We look at the foundation material in the headwater regions, such as in the mountainous regions around here. We have rock close to the surface. If we go, say, east of here onto the plains, then we get more alluvium and it's deeper. And we run into problems. This figure illustrates some of the problems too. We have alluvium through here. On the floodplain, we have finer material, which may be still alluvium, but we have more silts and clays, and also we have vegetation, which can add difficulties. The main design questions are, what is the peak flow in order to keep the bridge deck above that? Will debris or ice accumulate at the bridge crossing? Which parameters to use in the estimation of scour depth? And I'll illustrate some of these. What are the limits of rational formula that exist? When a model is needed, particularly for bridges or unusual designs of piers or abutments, and increasingly we're using numerical models to understand what is happening, and monitoring and management of bridge sites is continually needed. So Iowa, for instance, has got 5 crews which inspect all the bridges every 3 years. And they increasingly use things like drones. Before they had to have trucks with articulated arms that can go under bridges and so forth. And they measure scour, and scour reduces the friction bearing length. We have a graduated approach in design, as indicated through here. So there's standard forms, which really the DOT should do scour tests on all the standard forms to know type of material, what their behavior would be, and more complicated forms that can arise. And so we have a graduated approach. Increasingly, we have a rational formula, scour around a cylinder, to a system model, where you need a model of some form to understand what the flow field is doing and how the bed is interacting with the flow field. So this is the recommended approach. So the semi-empirical relationships that you find in HEC 18, which is the leading Federal Highway Administration guide on scour, The rational equations apply well enough for simple pier forms, but as soon as you get complicated like this, you run into accumulation of woody debris or ice. Things can get more complicated quickly. So you have this sort of approach, rational approach at the top, and the leading approach, in my opinion, is by Shepherd and Melville, which is merged, which is only partially included in the Federal Highway Administration. Some of the earlier models they used for estimating bridge scour depth were inadequate, in my opinion. And then more complicated forms, you have to resort to modeling of the whole bridge system. That was illustrating accumulation of something, woody debris, which changes the pier shape, complicates the flow field. And I'll show that bridges in Nebraska are built too low. Road bridges are. Rail bridges are better. It's cheaper to build a lower bridge than a higher bridge, but you need to allow enough distance between accumulation, particularly of ice. Part of the challenge of climate change is the frequency of these events diminish, and so the designers of these bridges tend to neglect woody debris or ice or treat it as a nuisance. But in fact, there's not enough clearance given, certainly not in Nebraska, in my opinion, between the bridge deck and the water level. Woody debris increases the load on bridges, so there are a lot of bridges fail because the drag on the woody debris transferred to the bridge. Or you have, like Pierre showed yesterday, with a debris flow, and the equivalent to debris flows are basically ice runs on rivers here, can lift the whole deck off. So I've seen a bridge in Nebraska where the whole deck was lifted off, floated off downstream about a mile and then just dumped on the bed. This is a rational approach, and a rational approach is this depth of scour equals all these cave factors around here, which take into account different effects. And so this is from Melville and Coleman's book on bridge scour. This relationship has been updated through recent years through collaboration between Melville and his group and Max Shepherd from University of Florida. But this is the effective depth size factor. So again, wide, intermediate, narrow. Narrower, as I showed before, you get the deeper scour. This is sediment size factor. If you have larger sediment, it tends to dissipate a lot of the energy, don't get as deep a scour. So you have coarser sediment here, less deep scour. Fine sediment, it can scour away quite happily. You get that factor. The type of nose you have on the pier, include that in terms of scour. So it's very approximate, but approximation is good enough. Alignment of a rectangular or a circular pier you can include through here. Shape factor here. Flow intensity factor, clear water live bed. So you have like we found with contraction scour, it peaks around the limit of clear water scour, then drops off as you get into live bed scour, then picks up again, particularly picks up where we have antidunes being formed and flow becomes supercritical. And the time factor, it takes time for scour to develop, and so takes more time for clear water scour to occur relative to live bed scour. Plus, you have to consider the time factors of the flow processes and the geotechnical failure. And that's where a lot of the research frontier presently resides. So we have these sorts of plots where people have done, such as me, have done what happens if the bed is armored. And you put a pier in that. And so effective armoring, non-uniformity of sediment pulls the scour depth down, as you can imagine. You get the coarser particles on the bed surface, continue the clear water scour for a bit, but if you get coarser particles armoring the deepest part of the scour runs to a halt. And so these sorts of figures have been developed over the years by various experiments and so forth. It's very hard to do field work. This is time development, scour depth, and time development, and clear water scour, live bed scour, and so forth. You get a complicated figure like this. This is a three-dimensional figure, which all I want to do is to show you it gets complicated. It's the simplest experiment to do in a lab, but the flow field is very complicated. Abutments, we look at abutments, this part of the bridge. So just to sum up, the flow field is very complicated around a pier. Junction flow, which is the most complicated of flow fields, where you have a rigid body perpendicular to a flat surface. A lot of turbulence generated, 3D flow situation, very unsteady. As you move toward abutments, we have to consider typically more the geomechanical effects. Geomechanics, these things, the scour deepens, but the failure is actually a geomechanical failure. There's just not enough support, geomechanical support for the bridge. This is the friction-bearing piles, piers to stand up. On abutments, as we saw with in-stream structures such as Benway weirs and rock veins, doesn't take much scour to destabilize slopes, and you get these structures failing. And this is the weakest point of the bridge, and this is the point, again, at the frontier, what I call the frontier of ignorance, which is one step beyond the frontier of knowledge, where you don't know what you're doing, really involves both hydraulics and geomechanics, as Pierre, in fact, has pointed out in many slope stability problems. So we have slope stability problems both with bridge abutments, but all earthfill embankments, dams, earthfill dams, levees, and when they're used as approaches to bridges. So we have the things that are complicated. In this particular example, there's an earlier example where we have an abutment encroaching into the main channel. The flow field still is quite complicated. We get a shear layer between the main channel and the floodplain. We get eddies, get turbulence, large-scale turbulent structures generated through here. We get contraction flows. And it doesn't take much scour depth to develop here before this becomes destabilized. But as I point out, how do you model earthfill structures in the lab? And this is a part, again, where we're at the frontier of ignorance. So it's complicated by soil type, vegetation type, accumulations of stuff, woody debris, ice, erosion process, and the timing of the different erosion process, the timing of the geotechnical failure, and the scour depth development, and the variability of structure and site. Typically, bridges are not perpendicular to channels. They often are at some angle to a channel and so forth. So if we look at an abutment scour, this is the most common type of failure here. So this sort of failure you see readily. 90%, this is the most common failure cause of bridges over rivers, is the abutment washout. So the abutment is breached here so the flow can go through, so it reduces the velocity of flow through the bridge waterway. So we have various considerations. One is the abutment column has to also, it's exposed, has to remain standing. The abutment column is built in this is a spill through abutment, sits here, so the bridge deck, the beams sit here. Typically the beams are placed freely without support, without, I should say, being anchored down. So this is a free support for the bridge deck, so it can allow the bridge to expand in warm weather, cold weather decrease. And you've got different types of soils and so forth. Different types of abutments. And typically for small channels, we have rectangular abutments. So if you go up the Big Thompson, you'll find over those small bridges. And people have built small rectangular vertical wall abutments. And typically they put riprap around it, rock around it. This is the largest channels, typically spill through abutments. These are earth structures because they're cheaper. And the abutment column sits in here. And in between, you might have wing wall channels. These are relatively small channels, but I hesitate to say because sometimes these are used on bigger channels. And these may be where the wing wall encroaches on the main channel. 45 degrees is typical. And as I'll show soon, these things can fail geotechnically too. But you have different types of abutments. This is the large river one, very common, relatively common. Occasionally you'll see this on small creeks and so forth, when people don't know exactly what they're doing because you create larger blockage flow. This is an abutment column. This is called a standard stub column, which most of the DOTs use. You have friction bearing piles and pile cap here. This front views, side views, and so forth. This is a 1 to 30 scale model to show you what it looks like. This is what we would put in the flume, and the indentations where the beams of the bridge deck sit. We have a wing abutment like this. Again, you have piles like this supporting the weight of the wing wall, and the bridge deck beams sit here. And this photograph here shows you what it looks like at model scale. Again, the bridge sits in the notch up top there. And so your job as a hydraulic engineer is to figure out how high that should be, how high the bridge deck under lower stringer should be above the peak flow used for design, and how long the piles need to be to bear the weight of the bridge and the part of the bridge and the column there. What complicates things too is you can have various forms of scour. These are experiments done in Iowa where we have in this case, a rigid floodplain, maybe it's vegetated, doesn't erode as quickly as the main channel, and you get the deepest scar in the main channel here. The flow comes over here, you get rollers formed. If you make that erodible, as I'll show later, then the scar changes. These days we have more instrumentation, but just to point out here the complication of the flow field in plan view, and this is illustrated using large-scale POV, which is a method that we use increasingly these days. So you have the flow contracting around here, you have turbulent structures and so forth, and the deepest scar is in the vena contracta for this type of spill through abutment below the downstream edge of the bridge. If we have to consider the erodibility of the floodplain, we very quickly end up with three conditions of abutment scar. The first condition, where the scar is limited to the floodplain, particularly if the abutment is shorter, and the scar will happen on the floodplain. This happened on I-70 bridge. There's a big scar hole which they turn into an environmental pond. Then you can have breaching, as indicated through here. So modeling that is still a similitude challenge in hydraulic modeling and in numerical modeling too. And then the third condition is where the abutment column is exposed. The abutment column has to still keep standing. You treat it as a pier. So you have these multiple scar conditions to deal with. So abutment scar, people have not tended to do as many experiments on abutment scar as pier scar, because first of all, you need a larger flume and you have various types of scar. So this is sequenced here, just illustrates the type of scar that can occur that when the floodplain and the abutment approach are erodible. So you have flow, contraction around there. It starts to eat into the embankment, the soil embankment behind the abutment column. Bridge deck is still standing. Eventually you have a failure like that. The deepest scar is out here in the vena contracta area. Here, vena contracta is more important for spill through abutments and wing wall abutments. Same thing for wing wall abutments. Here you have an encroachment of flow behind the wing wall, and this particular experiment ended in that situation. Wing walls can be supported by piles or circular piles or H piles or sheet piles. Sheet piles are problematic because they create a rigid structure at depth. They're cheaper. So this is another experiment where we have an erodible embankment and you see breaching of the embankment and you get a condition like this. So the abutment is out here, the earthfill approach is here. So modeling the earthfill approach is quite a challenge. You can get all these three conditions, and I won't go into the equations up here, but basically the alpha factors are amplification of contraction scar. The C relates to contraction scar. If you can estimate the contraction scar, the turbulence generates what's called a corner scar, as I call it at least, which it doesn't take much to destabilize the approach embankment, the earthfill embankment, and you get a scar form developed. If the floodplain is fixed, like there, you get the scar in the alluvial main channel. If you increase the unit discharge, you get the scar migrating out that way and becoming larger. If you have erodible floodplain, you have the embankment failure, you may get an erosion here. This is a vena contracta depth compared, well, for a spill through abutment. And again, the size of the scar hole will get larger depending on the unit discharge ratio through here. In determining abutment scar is more a geotechnical problem, and you can estimate the scar depth from geotechnical considerations, slope stability considerations, than hydraulic considerations. It's too difficult hydraulically to estimate, in my opinion, the scar depth. Too many factors involved. Also for wing walls, you have to be very careful, because if you get erosion, you get geotechnical instability behind the wing wall abutment. The material will slough out below the abutment. If you have sheet piles, you can hold the material somewhat. Then you get breaching very quickly behind the wing wall abutment here. But if it's on piles, like I showed that one layout, then very quickly you get scar deepening here, hydraulically forming, triggers a geotechnical failure inside the abutment. And so often when you're inspecting bridges, if the bridge has a wing wall abutment, you need to check behind the abutment itself to be sure that cavities do not form. This is a busy slide, but all to say there's a procedure for estimating three different scar conditions. But more research is needed to prove these values. This is just a recipe. Basically, the amplification factor deals with the corner scours greater than the linear contractor scour. But I've become, over time, recent years, less convinced about this method of approach. Rather, it's a geotechnical failure. It doesn't take much scour to destabilize the slope. Slope fails. The average velocity across the bridge opening decreases. You get less scour. If the scour breaches, then you get no deepening of scour, but you have failure of the bridge itself. So there are amplification factors which we developed from contraction scour. This is the amplification factor for that type of situation shown up there. And I'll show two of these, and I'll get onto some of the similitude issues. These are wing wall abutments, the amplification factor. And the amplification is based on Lawson's contraction relationship, which I think is not right. So this requires more work still, but it's very hard to do in the lab because of the large flume that you'd need to include at reasonable scale the abutment. So the scale of the lab and the lab equipment is a factor in these sorts of experiments. So some of the advances and challenges that we face. First, similitude, instrumentation, and hybrid modeling. These are advances. So similitude relates to actually more challenges than advances. So we don't model flow rotation that well. We don't model erodible material, like earthfill embankments, that well. We don't model material strength that well. Instrumentation, there are all sorts of new instrumentation, as well as we can store a lot more data than we could before. And increasingly, we're using numerical modeling to look at the flow field and how it varies. We have this tool in our toolbox, numerical models, increasingly to explain or show us what the flow is doing. Sometimes, as I've indicated, the advances and the challenges are coupled. If I take flow similitude, these are really difficult for particularly abutment scour. We have similitude of the flow field, which is open to question in small scale models. And we have failure of the earthfill embankment, as you see there. So modeling the material that creates the embankment is an issue. So we look at these three length scales typically in most experiments. You take a simplest experiment, the flow and scour development around a circular cylinder. We have the cylinder diameter, we have the diameter of the bed material and the flow depth. We have those lengths to replicate, which are very hard to replicate to meet all these criteria. The approach so far has been to forget about turbulence, except the horseshoe vortex, which really doesn't contribute to scour deepening, in my opinion. So this has not been that well modeled. Not also been modeled very well has been the material failure of it, and I'll get some details here. So people have resorted to full-scale experiments on scour development. This is a hydropower channel in New Zealand, and a cylinder was put in, and they allowed the scour to develop, and they measured the scour. The scour was never as deep as what you find in the flume, largely because of the turbulence is not as over-modeled, is exaggerated in strength, I should say, in vorticity in the model. But there's been various large-scale experiments. The USGS had a large bend flume in South Carolina, which they quickly abandoned because the amount of work that was involved to set up experiments and the time involved to get a data point was quite large, and it really didn't show all that much. Early modeling focused on the approach flow and horseshoe vortex. And the good thing about this, no matter what the material is here, whether it's sand, snow, the scour depth typically is about, at most in the lab, about 2.3 times the diameter. That's the rule of thumb that I often use. Doesn't matter whether you use snow or rock. If you wander through here, snowshoe through here, look at scour around pine trees, you never see a scour depth greater than twice the diameter of the pine tree. So no matter how complicated the flow field is, the scour depth doesn't change, provided you've got uniform material. If you have non-uniform material and get armoring or layering of material, then things get more complicated. So early focused on the front. Now we focus both on the front and on the whole flow field, which we need numerical models to show us. And as we discussed yesterday, increasingly these numerical models are showing us more about what the flow field looks like. In physical modeling, we've neglected Reynolds number and I'd say Euler number. And these numbers, as I'll show, influence vorticity strength, which is greater in the model, the lab model, than in the full scale, and the frequency of vortex shedding. You get more vortex shedding in the model than you do at full scale. And therefore, they influence values of scour depth that you see in the lab at small scale than in the field. This is just an application of the Euler number. Basically, you have a rotation, a vortex rotation here, normalize things here, and you get a stronger, if you scale, as I'll show soon, the velocity with the Freud number or the Shields number, you get a larger velocity compared to the length scale. The velocity ratio is much, depending whether you define scale in terms of prototype over model, a different type of vorticity in the model in the lab. So narrower cylinders, such as you see in the lab, produce more stronger vorticity and stronger flow depth, scour depth, and they create more frequent eddies, separation eddies or vorticity structures than you see in the field. This figure here is very important. This is the Struhel-Reynolds number. This is Reynolds number across the bottom. Across the top is Struhel number, which relates to the frequency, the eta of shedding of vortices. So this affects the shedding of vortices. So Reynolds number is important in terms of the frequency at which you shed eddies. So as you see, as I've indicated in blue here, it's inversely proportional to, or frequency is inversely proportional to D if you keep the Struhel number about 0.2. If you go here, which largely depends on the roughness, then the frequency can be highly variable, which adds complications to scour depth estimation. So narrower piers create more frequency, more frequent eddies, and the vorticity of the eddies are larger than at full scale. You can show that if you have a model 1 to 10 scale, you model the geometry a tenth of the prototype, or you have the inverse, the prototype is 10 times larger than the model. So you have a length scale that's 10, but the velocity scale is based on the loose bed scour experiments on the Shields number parameter. And so the velocity scale is proportional to the square root of the length scale shown here for Freud number. So you've got to be very careful. So I wonder sometimes whether Freud number is appropriate for modeling vortex flows, drop structures and so forth, where you deliberately set up a vortex flow because you're exaggerating the vorticity of that drop structure of the vortex flow. I'm not sure that the lab models capture what's really going on with in that case, the structure design. When you have vortices, I'm not sure that the lab model captures really what's going on fully with the turbulent structure. Look at the earthfill embankment. Scour triggers failure, and then you have a slope stability failure. So if you want to model that in the lab, you have to model the soil strength, which is a problem. So this is actually, I think, abutment scour, as I point out, and scour at in-stream structures such as Benway weirs and rock lanes is more of a geomechanic problem than a hydraulic problem. You can calculate this scour depth based on the stability of the material forming the structure. It doesn't take much, about an inch and a half before the slope, typical lab model, becomes unstable, and then you get a failure, which then reduces the velocity. The velocity, you may destabilize the rock, the armor on the surface, which then causes a little bit more opening of the area, reduces the velocity, reduces the scour. Plus, you have the material on the, if you have a rock vein, for instance, that's rock, just a rock pile tumbling into the scour hole, that the rock will remain in the scour hole and armor the scour hole, so you won't get much deepening that. And that's part of what the study with Drew and David and Nathan was about, to design these, to have a sort of allow this to occur, have a sacrificial length. And most bridge designs do include if you design an apron, you should include a rock apron to limit the scour depth here. Putting rock on top of soil doesn't do anything. I mean, maybe good for preventing erosion of the soil by flow, but you're adding dead weight onto a slope, and that slope is going to fail quicker, as I showed in an earlier slide, than if you had no rock at all. Erosion of the soil materials very quickly. Modeling the strength of ice, for example, is very important. This is comes up frequently, particularly if you're in Canada, designing bridges. You want the ice to fail in flexure, which is as I'll explain tomorrow, is less than one of the weakest strengths of the ice. But to get that sort of in the lab, that sort of failure is a challenge. Still can be done. It's used a lot in ice design of ice-breaking ships and so forth, and so on. So if you have an abutment like this with an erodible floodplain, erodible abutment, you get this condition, as I've shown in the pictures here. But how do you model the strength of the soil? So this is a case of pure sand, and you have what Pierre called pseudo-cohesion. If you add water, you have surface tension, which allows vertical faces, even in sand, wet sand. So you can use wet sand to model an abutment. Well, things will happen much quicker, but you'll get a sense of what happens. Once this opens up, you can imagine the average velocity through the bridge opening decreases. So modeling the embankment is very important. Timescales are important. Scour and failure here. And the failure here is not slope stability necessarily, it's more undercutting of a bank, and the chunks of the bank drop down. So you can use wet sand as a model material, but you have to be careful about the timescales. Those are the background, but if we have an embankment, this is a flume in the hydraulics lab at the University of Wyoming, Clearwater Scour, we have an erodible tip on an abutment. What happens if we strengthen that abutment by adding material to the sand to make it stronger? We vary the strength of the earthfill. And so we did a series of experiments in Wyoming where we had an abutment, and these are the dimensions of the abutment, and the tip we had an erodible nose. We used sand, and we used sand mixed with silt, and we compacted it at the right moisture content. So it's more of a geomechanics problem, again, than a hydraulics problem. The rest of the abutment we modeled as rigid, and we coated the abutment with rock riprap, and we did experiments without any riprap as well. Well, we controlled the strength of soil using geotechnical compaction and shear strength measurements, so we could get the shear strength of the soil at lab scale and compare that with the scour depth that we measured. These are just photos of some of the instruments that we used in controlling the scour. So this is what we saw. So the nose, which was erodible, scour begins at the upstream where the velocity is greatest. Turbulent structures here, and very quickly you can erode through, and you end up with a failure that looks like this at the end. And what we found is the strength of the soil governs this, or influences the scour depth. And the soil didn't fail in this particular case by slope stability, which of a rock pile it would fail through slope stability. You don't get undercutting of a rock pile, you get slope stability issues. But when cohesion is important, you get block formation. It's like a bank erosion and undercutting. It can occur quickly. And so if you add rock, the rock that I have here doesn't improve the stability, it just adds weight to the soil here. It affects the scour depth because this rock will end up in the scour hole and partly armor the scour hole, partly, and produce. This is a close-up. You can see the contraction of flow, failure of the erodible nose, and the debris from the riprap ending up in the scour form. And the bed itself was sand, I should say. I should have mentioned the sand. We've added more silt. We've strengthened the abutment. And this is the failure that we see. More complicated. Again, you can estimate the scour depth based on geotechnical considerations, not on hydraulic considerations. So I would argue that abutment scour is more a geotechnical problem than a hydraulic problem. Scale, abutment undercutting, this part of the abutment was rigid. These are kind of preliminary experiments just to show that strength of soil affects the scour depth that you have. So you get undercutting of blocks and failed blocks and so forth, as the top two photographs show. You get more of block undercutting failure. You can use, as I pointed out, sand. It adds surface tension, adds cohesion, but even that wet sand failed through block failure rather than slope stability failure. And these are the effect of embankment shear strength, plot of embankment shear strength versus scour depth. So if you had just sand embankments, you get this curve. If you had a fixed structure, fixed embankment, you get that light blue curve. And as you strengthen the if you strengthen the embankment, you get this curve here. Pure sand is here, but you've added and compacted the material, you get a curve like that. And somewhere between the two is where the truth is. Well, I would say the truth is likely in this particular curve here, which is far less than what you find is often reported in papers, where abutments are treated as rigid structures. If you treat them as erodible geotechnical structures, you get much shallower scour. They fail, but they are much shallower scour. So these are two bridges in Wyoming. You can see the geotechnical. It's opened up the bridge waterway. Contraption is basically limited. Very similar to what we saw in the lab in Wyoming, where the abutment failed. Not much scour out through here, partly because of armoring, but the geotechnical aspect. So the modeling of the soil strength is a challenge for us hydraulic engineers to do these sorts of experiments in the lab. You need a geotechnical engineer to work with you to model these sort of things. Instrumentation, well, I've showed before for example, all sorts of instrumentation and data management have increased. These are, again, images from large-scale POV, sort of shows you a long spill through abutment with the abutment column and the flow breaching behind the column shows you what the surface flow field looks like. So we can get that sort of information. We can do the hydraulics quite well. The challenge very much is the turbulence. We don't model that well, and we don't model that well the embankment soil strength properties. Those are challenges that remain with us. Hybrid modeling, basically the introduction of numerical models. You can run numerical models, which we did at Iowa, George Constanescu, graduate student, and myself, and get images like this for a very simple structure such as a circular cylinder in sand. You can show what the flow field looks like. In the lab, we tried with stringy type of flow field illuminator, but we get odd shapes like this where the material we put in stays together, but it doesn't really show you, as these figures do. Figures illustrate what the flow field is doing. So we tried in the lab to see what more the flow is doing, but it's very hard with dye because it disperses very quickly and mixes very quickly and is very unstable. So you end up with a numerical model as a tool in our toolbox, overall toolbox as hydraulic engineers, sediment engineers, to understand more about complicated flow fields. This is again from George Constanescu using attached eddy simulation CFD. Look at the flow field around a pier. And again, these are the most complicated flow fields that you will find. Junction flow fields, where you have a vertical structure coming into a horizontal structure, like a wing coming into a fuselage on an airplane, or a pier coming into a flat alluvial bed. Numerical models are useful. This is the Firswim's 2D model, just to show if we change the floodplain with how it affects the flow field. So you get information like this reasonably well. It doesn't tell you anything about the turbulent structures, mind you, because this is a very 3D flow field, but it gives you some insight about how the flow field is doing. The floodplain is here, main channel is here, and it sort of shows you how that varies. And last slide. And the last slide is to do with judgment. These days, and I teach this to hydraulic engineering students, undergraduate students, many problems, such as in Pierre's book on hydraulic engineering, which you have to size a pipe or a pier or something. And it typically ends up as an iteration problem. So if you don't know anything, you start off, you guess the wrong, and eventually after about 10 iterations, you get the right answer. If you have experience, you're good judgment, you can guess for that size flow, you need this size pipe, diameter pipe, and you can guess, and you might do 3 iterations or 2 iterations, and you got the answer very quickly. Judgment is required very much extensively in a lot of hydraulic structure design, particularly bridge structures. What I wanted to do gives you a sense of the complexity of the flow field, the challenges that exist, modeling the flow field itself, modeling of erodible material, modeling of ice is a problem. We have improved instrumentation than what we had 20, 30, 40 years ago. We can handle large amounts of data much more, and that's very useful. So the paradigm has changed in that sense. But still, in my opinion, judgment is very important. Thank you.